So this is just recapturing the last 2 or 3 lectures discussion and giving a summary of that. Let's say that you have an input signal, GA of t. You pass it through a continuous to discrete converter, and then you convert it back into a continuous time signal. And at the output, you have got G hat of t. What are the 3 different scenarios that can happen when you do this operation? So the first case is that we assume GA of t is band limited to omega m radians per second. I'll use that prototypical image. Of course, in reality, it will be whatever is the Fourier transform of the signal. But here is what it looks like for our example, that the top amplitude is A. Now, we know that to understand what happens with whether you do any folding or not, it's always best to think of the impulse sample signal. So the impulse sample signal which is given by Gp of t, n from minus infinity to infinity, G of n, where G of n is the output of this block, times delta of t minus n capital T. And if you look at the Fourier transform, the first main equation that you should always keep in mind is the Fourier transform of this impulse sample signal is given by periodic repetition. So if the Fourier transform of my original signal is GA of j omega, what we get is a periodic repetition of our original signal, GA of j omega minus k omega t. So the gap between 2 copies or multiple copies is 2 pi over t, and the scaling is 1 over t. So that is one of the key results that is repeated again and again. And then at the reconstruction side, we know that if the Fourier transform of this thing is represented as G hat A of j omega, then the G hat or A of j omega is given by Gp of j omega. So the output frequencies are input frequencies times the frequency response of your reconstruction filter. And this formula is true also regardless of whether your reconstruction filter is ideal or not. Okay. Now these are the 2 formulas, and then the 3 scenarios that happen are, the first scenario is that your sampling frequency is greater than twice your bandwidth. If that happens, then you can follow through each single step, but the end result is that if your sampling frequency is at least twice the maximum frequency in your signal, then the output Fourier transform G hat A of j omega, that is equal to, so in that case you satisfy the Nyquist criterion and your output is equal to the input, which means in both time and frequency. So that is the best scenario that you can hope for. The second scenario is undersampling. So omega t is less than 2 omega m. We are undersampling. And also there is no anti-aliasing filter. In that case, to figure out what is g hat a of t, you have to look at g hat a of j omega in terms of gp of j omega times hr j omega. Okay. And if the signal is made up of pure sinusoids, then the solution is simple. You can just look at the aliasing plot that we had done in the previous lecture. But if the frequencies are not just pure sinusoids, then you really have to look back at how things are folding. So for that, you first have to write down your GP of j omega, which if you are not satisfying the Nyquist criterion, then it's going to look like this. This is your omega t minus omega t, a over t, and at omega t by 2 and minus omega t by 2, you start having folding. Right? So, and then if your low pass filter is ideal, if your low pass filter is, let's say, an ideal low pass filter which goes from minus omega t to omega t, minus omega t by 2 to omega t by 2, then your j hat a of j omega, to compute that, you have to do this summation and then do the low pass filtering, and the end result will be, you will get something like, in this example, depending upon whatever was your transform, you will get this. And then to get the time domain signal, you have to compute its inverse Fourier transform to understand what will look like. So this is the case where you have aliasing, you did undersampling, and because of that you had to do aliasing, and to understand what the output will be, you really have to go through both GP and then the reconstruction filter. Now the third scenario, which is the case that really happens in practice, because in this scenario what has happened is that you have, these frequencies have been corrupted due to aliasing. You got higher frequencies folding onto lower frequencies, and your new frequencies have corrupted even your old lower frequencies. So the third scenario, which is really what happens in practice, is that omega t is still less than omega 2 omega m. So you are doing undersampling. But to avoid aliasing, we first pass GA of t through an anti-aliasing filter. And unless we clarify that, anti-aliasing filter is we'll assume it's an ideal low-pass filter with a cutoff of omega t by 2. So in that case, your GA of t first gets passed to this ideal anti-aliasing filter to get GAA of t. So the Fourier transform of this GAA of t which I'll call GAA of j omega, then you have to look at what is that. So this was your Fourier transform of GA of j omega with omega minus omega m to omega m, and you are low pass filtering that to omega t by 2 with a height of 1. So GAA of j omega in that case, it will look like this expression, minus omega t by 2 to omega t by 2. Okay, this is your GAA of j omega. Now if I pass this GAA of t through an ideal sampler and then reconstruct it, my output will be, so now my block diagram is going to be in this third scenario, GA of t, the anti-aliasing filter, GAA of t, then I have continuous to discrete with a sampling period omega t that satisfies, that is up to whatever radians per second we specify that. Then I have discrete to continuous with the same sampling frequency, and I get G hat A of t. And the question is, in this scenario, what is G hat A of t? G hat A of t in that case will be equal to GAA of t, which is, because now this signal is perfectly band limited, so my output will be exactly the input of the sampling operation, which is GAA of t. So this means that the Fourier transform of your output, G hat A of j omega, is equal to the Fourier transform of your anti-alias signal, which is GAA of j omega. So your output is going to be shaped like this, minus omega t by 2 to omega t by 2. Now if you compare it to the second case, in both cases you are losing information. In both cases you lose information. Only the first case, when you satisfied the Nyquist criterion and the anti-aliasing filter did not get rid of any frequencies, you did not lose any information. But what is the difference between the second case and the third case? In the second case, you not only lost high frequencies, this is the second case, this is the output of the second case, you not only lost high frequencies above omega t by 2, but those frequencies folded back and also corrupted some of your lower frequencies, these regions. So now you can't really tell, of course, the higher frequencies, but also you are not so sure about the frequencies that you are seeing in your reconstructed signal. There is loss of information and there is corruption of information. Whereas in the third case, where you put an anti-aliasing filter, there is still loss of information. Above omega t by 2, which is pi by t radians per second. Why is there that loss of information? Because you threw away those frequencies when you put in an anti-aliasing filter, and you are never going to now recover those frequencies. However, the difference is that those higher frequencies are not folding onto lower frequencies and corrupting some of the lower frequencies. So there is no corruption of the frequencies that are recovered. So the bottom line is that if you cannot ensure the first case, which is often the case, then it is better to do case 3 by putting an anti-aliasing filter. You will lose information, but in many applications, either the information that you lose, you actually don't care about that. For example, if you are sampling your voice signal for transmission over a cell phone, what you really care about is the intelligibility of the voice. You are not really interested in whether you can capture all the high-pitched frequencies in a person's voice. So in that case, it's perfectly valid to put an anti-aliasing filter. The typical anti-aliasing filter has a cutoff of 4 kilohertz. You put in an anti-aliasing filter, 4 kilohertz or 3.4 kilohertz, and it will cut off high frequencies. You will lose those, but you don't lose intelligibility. On the other hand, if you are not to even put in an anti-aliasing filter, then you will not only lose high frequencies, but the higher frequencies will fold onto lower frequencies, and you may end up even losing the intelligibility of the voice that you are recording. So this is an example of the 3 scenarios that I talked about, where we have a song, Katy Perry's song, and so the first case is very simple. The first case is you have the song that is recorded without any the sampling rate perfectly matches the maximum frequency in the signal. It's sampled at 44.1 kilohertz, and what you hear is the song that you're used to hearing.
Do this, 'cause I'm coming at you like a dark horse. Are you ready for a perfect storm, perfect storm? 'Cause what's in mind, what's in mind?
Now I hope you are paying attention to some of the beats or some of the words in the song, because what we are now going to do is take the same song and sample it at a much, much lower rate. So I'm going to actually undersample it by a factor of 6. I'm going to sample it at 7.35 kilohertz. But I'm not going to precede that with an anti-aliasing filter. So what we'll have is not only that the higher frequencies will be gone, but those higher frequencies are going to fold back and also corrupt some of the lower frequencies. Now I want you to pay attention to this, because in the third case, then we are going to do the same thing, but with an anti-aliasing filter. And what we are hoping to see is the difference that when we don't have aliasing, how does the song sound like compared to when we had aliasing. So this is the case when we have aliasing, no anti-aliasing filter.
Do this, 'cause I'm coming at you like a dark horse. Are you ready for a perfect storm, perfect storm? 'Cause what's in mind, what's in mind?
Now, of course, some of the things that you notice in this song is that the vocals are more or less intelligible. And the reason for that is that, as we talked about earlier, intelligibility in voice is mostly contained in lower frequencies. So you don't lose that much information, but you did hear some hissing sound in the song. And of course, the song sounded like you had really increased the bass on the song because all the higher frequencies were being killed. So it wasn't sounding that crisp. But some of the artifacts, some of the hissing was actually due to aliasing. I'm going to now replay the same song with the same sampling frequency. But the only thing that is going to differ is that the song will have been passed through an anti-aliasing filter, and so there will be no folding of higher frequencies into lower frequencies.
Do this, 'cause I'm coming at you like a dark horse. Are you ready for a perfect storm, perfect storm? 'Cause what's your mind, what's your mind?
Now, they of course sound very similar vocally, but some of the hissing sound that you are hearing, which was really due to the higher frequencies folding onto the lower frequencies. There is no other difference between the two sampling systems. They are being sampled at the same rate. In one case, I am passing it through an anti-aliasing filter. In the other case, I am not. Okay? And you can play these two versions again and again to compare them against each other.